Assalamualaikum warahmatullahi wabarakatuh and hope you in a good day. My name is Mohamad Asraf Shafiq bin Ashar and today I'm going to present to you my final year project presentation with the topic of fatigue crack growth analysis of welded high strength steel using sand specimen. My supervisor is Prof.Ir.Dr.Ts Engineer Yupiter Harangan Prasada Manurung and my co-supervisor is Yusuf Olanrewaju Busari. Hope you enjoy my presentation. The study of crack propagation of where the S460 high strength low velocity have not well established and limited resource regarding to effective strength of material. Crack propagation rate depend on the various type and factor. Moreover, the simulation will not have the same properties reflect to the experiment which tend to have more geometry. Due to that, the result of the simulation is not always correct. Therefore, the simulation result will be validated with the experimental procedure using crack growth measurement. Therefore, it is called for investigating where the S460 high strength low alloy steel specifically at the base metal and heat affected zone for its ability and feasibility to be used in industry such as automobile, offshore, and construction. The objective of this paper is to obtain the crack growth parameter such as the Paris law coefficient, which is the CNM, will help determine the metal crack growth rate toward the constant amplitude loading. Second, it is to accurate calculate of stress intensity factor by using the applied stress, geometrical factor, and length of crack. And lastly, to determine the crack propagation rate and fatigue strength of where the S460. Next, scope of work. The study focused on investigating whether S460 high-strength low-velocity crack propagation rate using single and notch tensile sand specimen. The primary goal of the study is to obtain an accurate result from the MSc Mark software by comparing it to the experimental finding as reference to investigate the fatigue strength of the specimen by applying constant amplitude loading, which will result to fatigue crack propagation. First is to construct welded S460 high-strength low velocity for the experimental procedure. Next is to perform the experimental procedure with constant amplitude loading on the welded S460 high-strength low velocity to study the fatigue crack growth parameter. Third is to conduct the analysis on the data of the experimental procedure to satisfy S460 fatigue crack growth parameter. Fourth is to perform finite element method simulation on MSc Mark software with the parameter obtained from the experimental procedure. And lastly, to conduct an analysis on the simulation result. Again, experimental value to verify the accuracy of the simulation. Methodology. This chapter will go over all of the pace and process that were executed in order to accomplish the study. Procedure is shown to achieve the objective of the topic, where research methodology used provided an efficient flow of how the research was conducted. In general, the process to carry out this study can be categorized into experimental procedure and simulation. To achieve relevant result, these approaches were taken to carry out this study, where it includes obtaining experimental result and use the data to perform simulation. The experimental procedure consists of mechanical tests which require to obtain mechanical parameter of welded S460 steel, especially at the base metal and heat affected zone. However, the movement control order MCO 3.0 forced to stop the experiment. By that, we have made initiative to using the data from the literature to run the simulation. The simulation output will then be compared to the data from the experimental in the literature for the verification. These methods are necessary to achieve goal set in the objective of the topic. This is the flowchart of this topic. First, we will go to the welding process. Welding process is the preparation process for the welded S460, where we will use robotic gas metal outwelding to make the joint. And after complete welding process, we will cut it and make it into sand specimen. Then the sand specimen will undergo the fatigue crack test. However, due to MCO, we cannot finish the experiment, but we can obtain the data from the literature. After obtaining data from the data parameter from the literature, we running the simulation for base metal and heat affected zone. Then we compare the simulation result with the result in the literature. After that, we validate the result with the same load. If it's okay, then the comparison is good enough and legitimate. Welding process, this is the preparation for the welded S460 specimen. It comes in plate with 10mm thickness. The edge of the plate need to be grooved 30 degrees for the single V weld joint using this milling machine. After the process, the bevel angle, this is the bevel angle of the groove, was checked using this cam type gauge to ensure it is exactly 30 degrees. It is also required to make root face with a dimension of 1mm. This is the root face. The root face is the surface member included in the groove design. This is the groove design. While the root gap with 1.2mm is the portion where both specimens each other more closely. It will have the welding friction in both edges of the specimen. The root face is the surface of the groove next to the root joint that help avoid collapse of welding through the gap. After finished grooving, the two plates of the S460 high standard aerospace specimen will be wet using robotic gas metal arc welding. The preparation of weld depends on the size of the filler, which is 1.2mm in diameter. First, both specimens will get through welding at the edge to attach each other and to avoid inaccurate dimension of the root gap after setup as shown in this figure. Then the specimen will undergo welding process. The welding nozzles must be set at the root gap before the process begins and need to check from end to end to ensure the nozzle will stay on the part to avoid defect from happen. Then this is the welding process result. As we can see, we have three parts. We have base metal, we have the base metal, we have the heat affected zone, and we have the wet metal part. In this study, we focus on two parts, which is base metal part and the heat affected zone. Performing corrective opening displacement CTOD experimental positive require welded S460 high standard LC specimen. The fabrication of the welded S460 need to achieve the dimension as shown in this figure that will be used as the sand specimen in the experiment. The specimen model was created using Katia B5. The welded specimen will be cut into dimension as shown in this figure with a notch using the water jet cutting machine. Water jet cutting method was chosen because its ability to cut thick and hard material precisely without affecting the material properties, and it is also more versatile and effectively can cut complicated shape. The fatigue crack test will be evaluated according to ASTM E647, which is the standard for the test measurement of the fatigue crack growth rate. The sand specimen will be placed in between these two gaps, with the crack gauge placed in the middle of the notch where the crack propagation takes place. The specimen will be applying constant amplitude loading by the machine. Simultaneously, the data will be collected from the crack gauge to measure the number of cycles corresponding with the crack length. The result will be in the crack length, again number of cycle graph. The graph is so resourceful for the simulation to take place because it will provide the coefficient of Paris law of this specimen. Finite element method FEM simulation. MEC602 will be used to construct finite element modeling to simulate behavior of the complex material specimen under large deformation and strain. From here, preliminary result can be obtained and compare validity with the experimental in the literature. The simulation will involve 3D model construct in the MEC602 reflect to dimension specimen in the literature. There are 4 steps in finite element method simulation. First step is to create model geometry and material properties. The model geometry will follow the literature specimen dimension, which is 100mm in length, 60mm in height, and its thickness is 12mm. In this simulation, 3D model need to use tetrahedral element as shown in this figure in order for the remeshing to take place. The tetrahedral element is used to the model to create fine mesh. A fine mesh will result to more accurate result as it has more point of load. The simulation model must represent the material properties used in the literature in order for the simulation to be valid. The material elasticity or Young modulus for nylon nickel 70 is 203.5 GPa and the Poisson ratio is 0.3. Next, the boundary condition. The model in the simulation will be applied with the tension force same with the experimental procedure for the crack propagation. It is the cyclic loading for fatigue process. In order to apply it, it needs to set the formula for the stress ratio. The stress ratio R equal to 0 defines that the model will be applied tension force from the original condition to the set applied loading, then will release it to the original condition as shown in this figure, where we apply the force until certain loading, then we release it back. In the boundary condition also, we will determine where is the crack propagation located. This is the crack propagation located, where the place it need to be clamped, and where is the load will be applied. Next step is define load case. For this simulation study, it is set for the total load case time to be 50 seconds and the number of steps to 100. This means the MEC6 will perform 100 remeshing steps with the constant of 0.5 time step. After finish set up the parameter, it is need to check and make sure there is no error on the model. Then it is ready to begin the simulation. And the last step is mesh sensitivity analysis. Before continuing further with the simulation, the identification for suitable mesh size for the simulation are crucial because it will affect at the end of the result. The model will be constructed with a mesh size such as 0.5, 1, 2, 2.5, 3, and 5 mm to identify the number of the cycle. The parameter input to the model of each mesh size are the same. The accuracy of the simulation relate to the size of finite element mesh. Stable element mesh provide more accurate numerical approximation. The mesh sensitivity was performed using MEC6 software by running different mesh size with the same material properties and parameter in the simulation. Each mesh size will indicate different number of cycles. This figure shows the graph of different mesh sensitivity applied in the simulation. A set range of mesh size from 0.5 to 5 mm is used to determine stable result in the number of cycles. Mesh size from 1 mm to 2.5 mm shows satisfying result, which it is more stable and steady than other, while 2 mm is the ideal mesh size for the study. Fine mesh size is not guaranteed it is the best for the specimen. The number of cycles for mesh size 0.5 and 3 is impracticable as it is not stable because the number of cycles is lower. Result and discussion. For this simulation result, the simulation is successful once the MEC6 show an exit number of 3004. It indicates the process successfully go through all the parameter and condition to the model without any issue. From the result, the MEC6 can provide the animation of the simulation. The increasing length of crack and the number of cycles can be observed through this animation. This is the beginning process of the crack propagation, and this is the end result of the crack propagation. Once the simulation finished, as shown in this figure, the number of cycles and the length of crack propagation can be obtained in the global variation of the crack variable. It is the end result of the simulation. In addition, the data can be fitted into a crack length against number of cycle graph, as shown in this figure. This graph helps to observe and understanding more the flow of the crack propagation of the simulation model. Simulation result. Due to the movement control MCO 3.0 to prevent the spreadness of COVID-19 virus, the experimental procedure to carry out fatigue tests of Welded X40 were forced to stop. However, the fatigue crack growth parameter was obtained from the literature review. It will be using nionickel 70, which is categorized as high strength low velocity with nominal yield strength 700 MPa and the tensile strength is 800 MPa. The analysis of the experimental result are presented in crack growth rate against stress intensity factor graph for the base metal and the heat affected zone, where the Panelist law can be used to determine coefficient of C and M. Reverse engineering has to be done to get the applied stress by using the stress intensity factor of base metal and heat affected zone. It is used to clarify the applied stress used in this study. The characteristic of crack propagation is determined by the coefficient of C and M from the Paris law. The coefficient of Paris law shows the slope for heat affected zone is smaller than base metal, represent the crack growth rate of heat affected zone is smaller than base metal. It also indicates that heat affected zone need more number of cycles than base metal for the crack to propagate. Due to this condition, fatigue failure will happen to the base metal first, then the heat affected zone if constant amplitude loading is applied to the specimen. This situation is because the heat input during the welding process to the base metal process have changed the microstructure, thus increase the hardness of the heat affected zone. Due to that, the literature experiment show proof that heat affected zone require more number of cycles for failure to happen, reflect to the welded S460 high strength low alloy specimen, the condition is expected to achieve the same condition, which is heat affected zone is harder than base metal. The number of cycles for crack propagation at the heat affected zone require more number of cycles than base metal. Further investigation with experiment procedure must be done to provide the exact Paris law for base metal and heat affected zone at the welded S460. The experiment will generate crack propagation rate against the stress intensity graph for each crack location with the same parameter to get the Paris law coefficient. However, the comparison in the literature between base metal and heat affected zone was unbalanced due to the applied stress are not the same. A better result can be achieved in this simulation by using the parameter which both have the same constant amplitude loading of 70, 80, 90 and 100 megapascal with the stress ratio of R equal to 0. As expected, the result from the simulation show that there is a decreasing number of cycles for both base metal and heat affected zone due to the increasing of applied stress. Referring to this both graph, higher applied stress indicate for lower number of cycles. From the simulation, it is verified that constant amplitude loading play a significant role to the fatigue rate propagation. The Paris law from the literature indicate the slope for the base metal and heat affected zone determine the crack propagation rate which affected on the number of cycles needs to achieve the fatigue crack. Discussion. Constant amplitude loading plays a significant role to the fatigue crack propagation of this specimen. The Paris law represents the slope for the base metal and heat affected zone determine the crack propagation rate that affect on the number of cycles to achieve the fatigue crack. The crack propagation rate is influenced by many factors which control the number of cycles needed for the crack to propagate. The residual stress is one of the factors come from the manufacturing process and after wet process that will decrease the material toughness. Besides residual stress, small crack, flow at the specimen grinding process and surface finishing also determine the toughness of the specimen. Wet specimen, especially at the heat affected zone, have different toughness than the base metal. It is the effect of the post-wet that result the increasing of hardness at the heat affected zone even though it is come from the base metal. The heat input from the welding process help increase the hardness of the specimen. These are the environment factors that affect the experimental result. The simulation process need to be verified with the experiment result data to know the legitimacy of the study. The result is influenced by the external factor that the simulation could not be able to deal with. The simulation process greatly help by providing the expected value, but it requires parameter that needs to come from the experiment itself. The simulation requires data such as coefficient of CNM of the Paris law, stress intensity factor, geometry, material properties, and constant amplitude loading, which generate from the crack propagation graph of the experiment. The simulation will apply the same constant amplitude loading from the experiment, so the result will be inline. However, the result of this simulation may have its error as it cannot put account the environment factor or the external factor that influence the crack propagation rate of the specimen. Conclusion and recommendation. Growing demand for the high-strength steel in the industry require deep study in investigating the fatigue crack propagation. Further investigation is needed to achieve fatigue crack growth of welded S460 high-strength low alloy steel. However, the result is expected to achieve the same condition as in the literature experiment. The heat-affected zone of welded S460 have a low crack propagation rate than base metal. Thus, it shows that it requires higher number of cycles with the same constant amplitude loading to generate the crack. The simulation aim to ease the work process need to be verified first to recognize the percentage error from the experiment result. The simulation unable to consider the external factor that influence the crack propagation. In spite of that, the simulation help with the range of expected value for the experiment. The recommendation for this study is to get through the experiment procedure to get the desired coefficient of Paris law and achieve all the parameters that lead to the crack propagation rate of welded S460 high strength low alloy steel. This experiment data will help reducing the percentage error for the simulation and make the data reliable to be used in the study, which help reducing cost, time, and work to be done. Thank you for your time. If you have any question, don't hesitate to contact me. Thank you.